Hi everyone, this is Jesse here from SkyCiv, and today we're going to be taking a look at a design example for a Weld group capacity calculation to the Eurocode 3. For this design example, we're just going to be using the Quick Design Weld calculator tool, which you can find in the Quick Design library by searching for Weld. And in this case, we're looking at the European standards, so you can click on European standards to find this tool. The properties that we're going to need for this calculation are the geometries of the weld section. So we have the property S here, which is usually what we specify for a weld. A 6mm leg length of weld is quite common. But in our design calculations, we're not actually going to use this value of 6 because we don't expect the weld to fail along this plane. We expect it to fail along this plane, or this is the most critical dimension of failure because this is the shortest dimension. So that dimension here, the throat thickness, is going to be 4.24mm, which comes from the calculation of S on square root of 2. Next, we need to know the plate thicknesses. We'll just assume something simple for this design example, but you can put in whatever you have in your design. We also need to know the material properties of the weakest plates, weakest steel members adjacent to our weld. I'm just going to assume the default here, which is S235 for the weld grade. Finally, we can add in the geometry for the weld. So I'm just going to do a very simple case here. I'm just going to remove the welds of this IPE 80 section, and I'm going to add in just a simple horizontal weld. So I'll make it 100mm long at a coordinate of 0, which doesn't really matter too much, but I'll make it 100mm long. And we can also, of course, put in design loads. So I'm just going to put in a few simple design loads, a in-plane force in the X and Y direction. And we'll just make our moment in Z 1 kN as well. We also have options like to perform a simplified or directional design approach. You can change the partial factor of safety and the weld type, and we have an option to show a stress graph. So I might just show the stress graph here so we can see what it does, and we'll run this calculation. So here we can see the design report. We have all the inputs summarized at the top of the report, a drawing of what our weld looks like here, and finally we start our calculation. So the first calculation is for the centroid of the weld group. And then we're going to also calculate the second moment of area for that weld group. And that's because we're going to need the second moment of area to resolve moments into shear forces on the weld group, which is what we'll compare when we're checking if the weld has sufficient strength to meet the requirements of the standard. So once we've calculated those geometric properties, we see here we're going to calculate the critical resultant stress. And that's going to be at the either extreme point of the weld, either the very extreme left point or the very extreme right point, and that's going to be just because of our moments. It's going to be generating more stresses at the ends of this weld. So we'll check those 2 points, and what we'll see is we'll find that the critical point is at the 100mm position. Just because of the other in-plane forces, it pushes the stresses to the right, and we can see that in this diagram here. So this diagram is showing the stresses as we move along our weld in this colored graph here. You can see it's not shifting too much. We'd probably expect a very similar value on the left here based on this graph. So the moment is definitely dominating the stresses in this weld. And if I go back up to this design table, we can see the calculations for how these stresses were calculated, and for each point what the stresses were. So we can see the value on the left-hand side was 590 newtons per millimeter, which is quite similar to the other value, but the other value does govern at 610 newtons per millimeter. So now we know the stresses that we want to design for. We want to calculate the weld capacity. So here we're going to take a few parameters. Like we just said, this is a summary of the main parameters we're going to need for this calculation. And finally in this calculation, we're just going to perform this simplified calculation here. So like I said, there's a simplified or directional approach. Right now we're doing a simplified method. And in this approach, we can calculate a capacity based on the throat thickness, the strength of the weld, and a few other parameters. We can calculate 881 newtons per millimeter, and we can compare that to our stress, to see that we have a utilization of 69%, and then in this case, this weld has sufficient strength based on this standard. Now we can also use the directional approach. So if I run the directional approach, I would expect that we might get a slightly better utilization than 69%, and we can run this and check it. I should probably turn off this graph so it runs quicker. But we can look at this. Let's run that again. And if I scroll down, or I can scroll on the right, okay, we have 57% utilization. So the difference here is because of the difference in the design method. So before, in the simplified approach, we are not looking at all the different stresses on our weld, whereas with the directional approach, we're looking at the direction of each different stress that's applied to our weld. And what I mean by that is I'm just going to take a screenshot so I can draw on top of this, and we'll see what each stress looks like. So we have this stress here, the normal stress, which is perpendicular to the weld. And that stress, if this is our failure plane here, that stress looks like this, goes this way. Next, we have our perpendicular stress, our shear stress that is perpendicular to the weld, which goes in this direction here. And then finally, we have our parallel stress, our parallel shear stress, which is going into the page. Now, what we'll notice here is we have this 3 factor on these 2 parameters here, whereas there's no 3 on the normal stress. Now, with the simplified approach, basically we're simplifying to have a 3 here as well, and we're basically kind of simplifying this equation to not be having, like, we're not having to look at all these different stresses. We're just simplifying this to have these stresses all have that same 3 at the front. So it makes calculations a lot easier. We don't have to look at the stresses, but of course it's less conservative because we're trying to make these stresses less than our strengths. And if we put a 3 here, it's going to make this equation larger than if we didn't have a 3 here. So this is only going to affect us if we do have normal stresses that are perpendicular to the failure plane. But in terms of calculations, it does make it a bit more complicated because in our calculations that we had before, if I scroll down, scroll up, we can see here that the shear stresses I'm calculating initially are in the X, Y, and Z direction. When I drew that drawing before, those went in the X, Y, and Z direction. We're going to need to slightly orient things to get those values that we need for the directional method. So whereas before we could just use the 610 newtons per millimeter and do an easy comparison, now for the directional criteria, we're going to need to perform some more calculations to determine what these stresses are. And we can see that here, where we calculate these stresses. And finally, we compare to see what the utilization ratio is. And of course, we can see that this utilization ratio is lower when we do this detailed method versus a simplified approach, which is more conservative. So I would expect that if we didn't have normal stresses, we wouldn't have a benefit. So maybe we can do a quick check on that and just have only in-plane forces. So if we had our weld going across, maybe let's just try having an X force and seeing what happens here. So let's just run this and we'll have a look. All right, so here we get a utilization of 1%. Maybe we can make this higher so it's more sensitive and we can see get an easier comparison. Okay, so we've got 57% utilization now versus when I change the design method, expecting the same. Let's see if it is. 57% utilization. So in this case, when we have the weld going purely parallel to the force, it didn't give us any benefit to consider the directional method. But of course, with a calculator like this, you can always just use directional lines. If you're not having to do the calculations yourself and you just have a software that does it for you, it's quite easy to get that extra benefit. So this was looking at the quick design weld grip capacity calculator for the European standard. I hope you learned a little bit about the differences between the directional and simplified methods and got some insight into how to use this tool for your own designs. If you have any questions about this video or questions about the quick design calculator, you can message us here and we'll get back to you as soon as possible. Thank you for watching this video. Bye.